tight 10 minutes for each of us, or for each of the presenters, I should say. So I propose that we go ahead, and I saw that Peter and Heiner and also Torbjørn had joined, so we should be in good shape. So I propose to hand over to Peter, and he has this overview of the Arrowhead fPVN project results. It's on the results, it's not the project itself. So please go ahead, Peter.
Okay. I will present two sets of documents. One, the first one is the deliverable for the Arrowhead fPVN project. And the other one is going to be the the Arrowhead fPVN handbook on industrial semantics. I start with the deliverable. So the deliverable is the official closing document of our work package 3. The title is Proposal for Updates of Major Industrial Data Models. This concludes 3 years of work led by Niels. Now the deliverable is divided into 2 major parts. One, the semantic interoperability across engineering standards, and the other part is the Arrowhead fPVN use cases. The interoperability part is divided into 3 subsections. One subsection is dealing with with standards which were included in the Work Package 3 program and are tested in use cases. This includes the ISO 23726, ISO 10303, ISO 15926, DEXPI, CFIHOS, and SysML. The next section is talking about standards which were in the work package program but were not tested in use cases. 2 of these, IEC 63278. This is the Asset Administration Shell, and the other is the Digital Product Passport. There were also standards which were originally not included in the work program, but we included them on the way, and they seemed very useful and valuable. 2 of these, one is the Arrowhead Framework Ontology, and the other is the Information Modeling Framework. Now the section about use cases details one use case and mentions another. The mentioned one is use case 2.9, the digital twin. The document only mentions this use case because it is already detailed in another deliverable called deliverable 9.4, and that is submitted independently of this report. However, we do detail use case 3.9, a process industry use case. This input we received from VTT, and this section details the BALAS system. The deliverable is concluded with the discussion and the conclusion part. The main topics here: alignment architecture, what are the strengths and the limits, that the maturity varies across standards, what is the role of tooling, semantic web technologies in an industrial context, our standardization engagement, and what are the steps towards industry deployment. These are the parts of this deliverable. I would like to go on to the other set of documents, and if you have questions, please pose them after that, or you would like to ask now. Whichever.
I think it was a sound glitch, Peter.
Okay, so no question at this point. Then I go on to the next set of documents. The next set of documents is, I'm going to show it on its place, is the Arrowhead fPVN Handbook on Industrial Semantics using IDO as operontology. Now this set contains 4 documents: a guidelines document, a handbook, patterns, and use cases. The guidelines is just a quick start reference for those who are not familiar with the topic, so they can get a quick insight into the concepts. The handbook contains the full rationale, methodology, ontology structure, and others. There is a separate document for patterns, kind of snippets, practical to use for modeling. And we have a separate use cases document which introduces a few use cases. Now, I would like to go into the detail of each of these documents, but I'm not going to show them here on the web page as it is rendered for online reading. Instead, I'm going for the PDF versions of these documents, which will be available as well. And I'm going to go through the table of contents of all 4 quickly. So the guidelines is just 17 pages. It contains the reasons for using W3C ontology. Then we talk about the property modeling workflow. And the document shows an example on CFIHOS semantics. That is it, basically, for the guidelines document. The Arrowhead proper, the handbook proper has 80 pages altogether. It contains an introduction part, a motivation for the work, methodology, how the work was carried out, competency questions for the work, the ontology architecture. We talk about the pattern library. This is not the library itself. This is how the library is organized through what concepts. And then there is a separate section devoted to lifecycle modeling, the standards alignment, and there is a separate section for open issues and pending decisions. We also have an appendix, alignment with IDO 23726.1-1 principles. So this is the handbook. Now the pattern library at 41 pages contains the property classes patterns, the quantity kind, and others, 7 altogether, but each section is organized around the same structure. So motivation, competency questions, context for use, structure and elements, descriptions of the pattern generation and validation algorithms, examples, and links to other patterns. And this is repeated for all the existing ones. Here we are expecting further input, and this is a live document, so we are looking to amend this document. Finally, the 4th document is the use cases document. This illustrates 5 applications altogether. These are the power transformer case study, the pump lifecycle use case, a semantic decomposition use case, a CFIHOS semantic use case, and finally, the process plant digital twin use case. Actually, this is the use case 2.9, which were left out from the deliverable because that was included in another one. But this very use case is detailed here in the use cases document for this work. Now, as a closing remark, I would like to show how the work is carried out. All the documents that I showed for the Arrowhead fPVN handbook are maintained on the post-Caesar Association's GitHub repository. The title is AfPVN Handbook. And this repository contains all the source files in text format, ASCII doc, actually, as you are seeing here in the screen. And the documents are themselves simple text files. And these text files are then rendered to the web page that I showed before. But the documents are also rendered to PDF. These are the ones that I presented to you a minute earlier. But we have output for ebook readers, Microsoft Word docx format, HTML, and the site, as I said earlier. So this is how the source is maintained through collaboration, version tracking, easy to see what happened and when. We had 411 iterations altogether since we started the work. And these works are then put into the official Post-Caesar Association website. And this is how it is presented. Also, let me add one more thing. The deliverable 3.3 is going to be open, and it will be available on the fPVN Arrowhead homepage at the deliverable sections. We have two previous documents. One is the major industrial data models, that was 3.1, and we had the major industrial data model semantic analysis. It was 3.2, and after we conclude the Arrowhead fPVN project, there will be a final inclusion of deliverable 3.3 as well. Okay, with this, I concluded my presentation. If you would like to ask questions, you can do it at this point.
Thank you, Peter. Any questions for Peter? We have a discussion at the end also, so there will be opportunities.
And I just added a link to the documentation on the Post-Caesar homepage. I guess it's only a few that has access to the GitHub repository, Peter.
Anyone wishes to have access, please write to Niels and myself. Niels will authorize, and I can actually add you to the access of the website. So just let us know, and the more people join, the better. We really want it to be a true collaboration.
And on the PCA web, the address is for the staging area, so you won't get to it unless you have the address. Of course, I hope that we can put it on the main.
Yes. I will also add the link to the Arrowhead fPVN deliverable site. This is it where you can download eventually. I think for the handbook, this is the official one, which I'm including, yes. And just in case, I copy and paste the site for the GitHub repository. You can take a look. It's closed at the moment. On the long run, it would be really nice to open it in read mode for everyone and write mode for the contributors.
Okay, let us go to the next item on the agenda, which is DEXPI. And just go ahead, Heiner.
Okay, I hope you can see my screen. My name is Heiner Temmen from the DEXPI organization. I will go into the presentation mode and present some, or let's say an overview over the results from the use case from the pump lifecycle story.
You are not sharing yet, Heiner.
Okay, it was... once again.
No problem. Yes, now I can see it at least.
Thanks, Jan, for the hint. Important.
No problem.
Good. And our task is about semantic interfaces with step application protocols, CFIHOS and DEXPI, of course, using IDO. And our pump lifecycle story begins in the process world. And the process, we have here a little example as a block flow diagram or as a process flow diagram. In the middle, a pumping unit operation before storing material and reacting chemicals. And between, of course, process streams, and we have the outlet port and inlet port in our example. And then we go to the process plant here as a little P&ID snippet. We know this is covered by DEXPI process. The below is covered by DEXPI plant. Here we have a pump system with the pump itself, a motor, measuring function to indicate the health of the pump. We have a storing vessel, and we have a reacting vessel. We have nozzles, and we have piping network systems between, and we have some properties for that as well, and we have some properties for the process as well. These two life cycle stages are covered by DEXPI, and of course we will, in our life cycle story, important to cover the asset world, in CFIHOS world, the equipment world as well, and of course the relation between the asset object and the plant objects. And that is important in our life cycle story. We will cover that. And here is an example. We compiled a new picture. In the BIM world, they have 4 quadrants, and the left 2 ones are plant functional entities and plant technical entities, and to the right, the realized functional entities and the realized technical entities. And we use the V-model for the demonstration. The lower level, we have then the realized technical entities as verification of the plant technical entities. And for the validation, if the concept does what it should, we have the realized functional entities to validate the plant functional entities. And now we put in our information structures. The main, that is the world of the process. Then we have the world of the process plant, which has the functional part and a technical part, a physical part. And to the other side, we have the assets as physical objects, and that's the realized plant. And here we have the producing plant, and these two pictures, they fit together if we use this kind of view for that. And now let's go a little bit deeper to the modeling results we reached with IDO. First of all, we have here the upper ontology list from IDO. I use the atmosphere picture for that. That is higher space from 10 to 500 kilometers. And DEXPI, we are at the bottom, at the ground. Let's say we need between the list ontology and the DEXPI world, we need additional reference ontologies. Most work has been done from Andreas Neumann. He is also in the call. Here we have perhaps additional extensions from LIS for property aspects, for data types, for value aspects, and how to relate to QDT. There is a result. And here we have some ontologies where we have all the properties in, where we have the classes from the process, from the specified plant, and from the physical equipment. And we need an ontology for assignment between the assigned properties. Important part, we cannot connect direct DEXPI to LIS. We need additional, let's say, reference ontologies between. We, from our life cycle story, we recognize which process classes we need for which required properties. We could use examples, that is for the process world, and the same for the specified plant. we have more. We see here in the middle there is a pump and the centrifugal pump. The blue part, the functional things, are modeled as system, and the green part, the physical specification, let's say the technical specification at that level, they are modeled as inanimated physical objects. And we have some properties for that. In IDO, we have to distinguish between the assigned and the dependent properties, and we related them, and we use cardinalities, of course, to say, okay, which classes can use, then it is 0 to 1, or perhaps the identifier, you have to use them, and then the cardinality is 1. And the same for the required asset. In our example, we have a centrifugal pump, we have the alternating current motor and a measuring system, and of course also there some kind of properties in our example. That is the part of our use case and how we have modeled them with the LIS classification. And this is one of the important results, that we have with the LIS object properties relation between the objects from the process to the plant world. We use for that LIS has participants and LIS participates in the other direction. And we have relationships, object properties to relate the green part to the purple part to the asset. We say, okay, the assets and the plant objects that are different objects, they have perhaps same properties, but they have also different properties, and in some properties, same properties, they can have different values, therefore that are different objects, and the relation between we use for that LIS implemented by and LIS implements. One important picture in the life cycle view. And here we modeled important modeling pattern. Here we use the results from Andreas and the special reference from the special reference ontologies. The picture is very busy, but only to say we have the classes in blue, we have the relations to ISO 5926 part 4 in green, we have the different instances, and we have the relations to LIS. And this picture fits. Here we have a good modeling pattern for our pumping unit operation. Of course, that is the picture, and behind is a turtle file. And the same, we have two kinds of property here in the demonstration. One as an assigned properties for an identifier, the assignment things and the relations to part 4, and the relations to the LIS classification, and in yellow the integration of the instances. The same we have done for differential pressure as a dependent properties in the language of IDO, and here we see, okay, we have the same with the yellow world. We include the world of QDT as well, and we check it against with restrictions against QDT and the unit of measurements which were used by DEXPI. Therefore, we have this kind of modeling pattern, and then I go to my conclusion. The pump lifecycle use case from DEXPI was successfully modeled. Important result. 2 steps to go. First is the transition of the reference ontology to the industrial readiness level. That is a task, I think, a follow-up task for the IDO community. That means that the reference ontologies were the first examples are modeled by Andreas. They have to go to an industrial readiness level, and the other step is we have to complete our DEXPI pump lifecycle prototype to a complete transition from a DEXPI export file to a turtle file. That is task in our DEXPI community. That was a quick overview over the use case pump lifecycle story in the AfPVN project. And with that, I will stop and I think, Onno, now it's your part.
Thank you, Heiner. We have a little bit of time at the end for questions and discussion. Hope we can keep that. Next one up is Onno Paap with the CFIHOS Semantics. I'm not bringing up the agenda again just to save some time. So please go ahead, Onno.
All right, thank you. I'll share my screen.
I can see it.
Good. So we have introduced CFIHOS Semantics into Arrowhead fPVN. Only later we did not join at the beginning. And CFIHOS Semantics is coming from CFIHOS, obviously, and I assume that you know all about CFIHOS. So we have decided to go to do a semantic team and to make an ontology out of the CFIHOS RDL and the data model. And so CFIHOS itself is a structured information handover across the lifecycle of capital facilities for diverse stakeholders. So what we mean is we can do handover from engineering contractor to owner operator, or from engineering contractor to the supplier, and the supplier back to the engineering contractor. And there are other situations as well, like front-end engineering and design, where you also have another type of handover. So the core components are a logical data model and a reference data library, that is a spreadsheet, narrative documents, that's really important to guide the process of a CFIHOS handover, implementation guide, and all of that is free downloadable from the CFIHOS website. You don't need to be a member to use it. And CFIHOS applies to multiple process and power industry globally, so that includes oil and gas, but mostly what CFIHOS is used for is chemical. Semantic transformation, so we have alignment with IDO. We make CFIHOS content machine interpretable and interoperable in ontology-based architecture. So you might think, yeah, why do you need semantic? And that is also what CFIHOS thought when we proposed it. They were like, yeah, we have a nice spreadsheet, we can work with it, that is not a problem. So why would you go semantic? For example, we have in CFIHOS a create script for databases, a relational database. So you can use that. You can even use it with Microsoft Access. But there was a challenge, and that was that we had not one standard on those projects, but very many different standards. So they show varied vocabularies, varied models, and there was a pure scalability in that, because you had to do point-to-point data mappings, and that is where an ontology is really good to make data integration for different standards. So semantics make meaning explicit and computable, enables consistent data interpretation across systems. Especially when you apply an ontology, then you can use that ontology to connect up various data sources. So I put two examples here: a central single database on an EPC project, also including input and output of supplier data. So on an engineering project, there can be many data sources, sometimes up to 40 kind of databases and spreadsheets and everything. So if you have a central database there, and semantics, of course, because of the variation of the data, that is really advantage. Another example is a central single database for all plants of an owner-operator to harvest millions of documents and transform all those documents to data and put it in a central database. And that must also, of course, be semantic because well, you have tens of thousands of distinct properties going on there, especially if you're going to harvest all those documents. And by the way, I'm doing a project like that as well for an oil company. So the benefit of semantic operability is to align the systems and share the semantic model. It supports automatic reasoning and cross-standard queries. Without semantic interoperability, digital efforts will be fragmented, costly, and hard to scale across asset lifecycle. So why did we choose for IDO as an upper ontology? Because CFOS is a perfect ontology, a domain ontology. Well, that is because we have all these other standards as well. So we saw DEXPI, we want to go to 10.303 and 15.926. So IDO serves as an upper ontology and it provides a unified semantic foundation for all these standards. IDO enables a star topology, so all these ontologies together, and IDO in the middle is a star, where all the systems align once to IDO instead of mapping individually. That gives us automatic reasoning because that is what IDO was built for, and interoperability without modifying our standards. So when you use the IDO, you can connect up to the other ontologies that have a different structure. Maybe even connect up to ISO 81246, and just work together like that. You don't need to change those domain ontologies. There's a way to do it. So IDO adds a semantic layer, enabling interoperability, while preserving the original content of the existing industrial standards, and that is the big advantage. So what we are going to do, we're going to do semantic transformation of CFOS. We are going to automate the ontology generation. We have test programs already. So CFOS data is automatically converted into an ontology. We are using a program, Python, to read the RDL spreadsheet and to make that ontology. We're not going to do it by hand, and we are not going to do any additions. We are just taking CFOS as is. Well, CFOS has a functional and physical separation, as you know. So there's the tech and the equipment side. IDO has that too, specified in the actual classes are meant for that. So it is a seamless connection to that. Also, we are doing property modeling. IDO proposed property modeling, so to standardize properties. We are doing that. We are standardizing thousands of properties that are coming into CFOS this year, and going to lift together on this new ontology. So we will have a rich queryable ontology. The resulting ontology enables reasoning, preserves CFOS intent, and supports cross-standard integration. This slide shows you how we do it. So on the left-hand side, there's IDO data model in Protege. Did not open all the classes there, just the main ones. On the right-hand side, there are the tabs of the CFOS RDL of the spreadsheet and how they map to IDO in the gray area. You can see the mapping, how that maps. So the domain ontology does not need to change. We map it with subclass of statements to the IDO ontology, and the subclass of inherits then the capabilities of the classes in IDO. So the key modeling concepts in CFOS semantics are normalized aspect-based properties. The idea came from IDO, and we are doing that now. Automated ontology generation. The program makes the ontology, and standard alignments and interoperability. So CFOS aligns with IDO enabling seamless interoperability with STEP and DEXPI ISO 5096 knowledge graphs. So what are the results and what are the practical values? Last slide. We have a technical ontology representation. So the reference data library is represented as an ontology. And of course, that's very nice to have. A website we are going to put up with the ontology so that you can traverse to it, much like the PCA ontologies right now. The practical interoperability benefits will be brought in. So the semantic representation supports cross-standards interoperability, reduces duplication, enables content reuse. We have the automated update program that will quickly reflect any updates, new versions of CFOS, or of your own RDL, of course. If you use a CFOS RDL, you are going to expand on it because you have many different things to add. So you get a program and you can generate the ontology for your own RDL. And a real-world integration value. Ontology-based interoperability delivers immediate value, especially in data integration. Ontologies and data integration are their thing of ontologies. So it is efficient and life cycle based. Thank you.
Thank you, Onno. We have one more presentation before we go to the discussion, and we are not doing too bad on the time. We are 1 minute behind, but that should be okay. So next presentation is how we have actually application of things we have done in a use case, which is part of the fPVN project. So, and that use case is a digital twin for a paper mill. So over to you, Torbjørn.
Thank you. So I will talk about digital twin based on knowledge graph or several interoperable knowledge graphs. You all know this picture. That's the problem. And what we have learned over time is that standards in itself is not a solution only that, because they live in their own silos, the standards also. So we need to make the standards interoperable. And that was work package 3, and I've been involved with Nils and the others there also, but I also been the architect of this use case called use case 2.9, the knowledge graph-based digital twin. And this is a very busy thing, but let's go through it a little bit, because this is what we have done. You see here we have an architecture where we have these quadrants, we call them, which is coming from a European norm 17632 BIM, and we deal with requirements and how they are realized with the specification, how the specification is used to produce or buy components, and how they are combined to a working solution. And the validation is between this, and the production or procurement is between here. And yes, that works. And we have been using IDEO, and we have gotten from DEXPI. We have got nowadays, we have an ontology for DEXPI that's coming from one of the companies involved in DEXPI called Semantum, but you saw on the slide from Heiner that there are now discussions of creating an ontology for DEXPI, which I think you should really be happy for, because that increased the value of DEXPI a lot. What's been done in workpackage 3 also is that we have automatically generated an ontology from STEP. It consists of like 1,200 clauses, and it covers the full life cycle. And that's the important thing. It's about the life cycle, how you realize the functions, and how you pick parts and individual parts, and how you replace them over time. We have also another ontology called Arrowhead ontology, which is about the cyber physical system. And that's coming from the Arrowhead microservice-based framework, but we have also created an ontology on that. We are using classification based on CFIHOS and CFIHOS Plus from PCA, and we are also using 15926-4, mainly, but that we're using the connection between these two. We use semantic technology, and we do deal with things like geometry, and we also have a viewer for the geometry of this plant, and we have an SAP HANA mockup, because we were not allowed to use a direct connection to the Stora Enso SAP. So we created a mockup that's dealing with maintenance planning and maintenance execution. So this is the architecture of what's been implemented. And you can see here we use the DEXPI ontology, and that's rather stable. Low change frequency. You change this when you're going to change the functionality of the plant. The STEP ontology is about the life cycle. This is mainly about maintenance and exchange of parts with the same functionality. And we have a high change frequency in the Arrowhead framework ontology, where we have a very rapid changing, because this has to do with the production. And we have used alignments. We have used DEXPI aligned to STEP and aligned to all of them are aligned. And we are using this star thing that Onno was talking about. We have used the upper ontology as the center of these alignments, and that has worked very well. Semantic interoperability through shared industrial identities. This is a more detailed picture of that. We have DEXPI, we have a semantic alignment layer, and we have lifecycle domains step here. And we do this by shared industrial identities. And we expect that to be in some kind of IDU extension later. And this is what Andreas also is proposing, how we should do this. These are patterns and things like that we will reuse. We couldn't wait for get all the patterns, so we have created our own patterns. But when we redo this next time, or even we could update this later for use in the plant. This is one of the core things. We have a 3D viewer, or called Cadmatic eShare here, and we have these components are connected to the knowledge graph representation of them. So we can click on things here, and we get to the things in the knowledge graph, and we could navigate this. Here you could see the 3D context. That's very important to understand when something is wrong or an issue. And here we have the system topology, as well as the life cycle history of the components. And this is working nicely. We are right now creating an end-to-end demo on this, and it's really successful. So key takeaways from this digital twin project part use case. We are dealing with semantic interoperability. We do have life cycle traceability based on STEP and temporal parts. We are using open standards. Some of them are ISO standards, some are like DEXPI coming from a consortia. We have very good IT/OT integration through the microservice-based Arrowhead framework. We are dealing with reusable knowledge graphs. We are not aligning everything into one ontology. We keep the ontologies as they are with their own semantics, and we align things that really representing the same thing in reality. That makes it really fast to implement, and we get business value out of this, even if with very few, like we align like 5% of the concepts, and then we can get like 60 to 80% of the business value out of it. We have also worked with GraphDB on digital twins for and it's a scalable, and we can add things, we can remove knowledge graphs, and so it's both flexible and scalable. We have also tried this talk to your graph to use natural language to talk to your graphs and put questions like when was this part realizing working in this function location and so on. That was it.
Thank you, Torbjørn. So let us just take a quick look at the agenda again. We have done the presentation, so we have at least 8 minutes left for discussion now of the results, and hopefully also some ideas on the way forward. And if it's okay with you, Jan, I would like to hand over to you for that discussion part.
Excellent. Thank you very much, Nils. Then I don't need to raise my hand. I think this was a fantastic kind of speed dating on how to see semantic operability working and built on the Arrowhead framework. Fantastic program. Really good. Very, very good. Yes, we have. I can switch off the recording now, so we get a more free Q&A session. So then I